In this video, we look at more examples of normal subgroups using the condition that a subgroup is closed under conjugation. So here we are going to be looking at large, infinitely many examples of symmetric groups and dihedral groups. So one thing we haven't done is we haven't used this equivalence definitions to look at more advanced examples. So as an advanced example, let's look at the subgroup generated by rotations in the dihedral group. Okay, recall that the dihedral group, which are the symmetries of an n-gon, has rotations, n rotations, and n reflections. And the reflections could be written as s times a power of a rotation, where s is some sort of special reflection. And with respect to this way of writing down the group, R has order n, S is order 2, and R times S is equal to SR inverse, which is a way to be able to multiply any two elements in the dihedral group written this way quickly without having to write down the polygons and actually doing it the hard way. So what we're going to prove is that the cyclic subgroup generated by R is normal in Dn. Note, it is worth pointing out in case you need the reminder, angle brackets R is a set, not an element. And it's not too hard to see. Remember the definition, it's all the possible powers of R. Since R has order n, it's R to R to the n minus 1. It is in fact a subgroup. Trying to prove that this subgroup is normal in the dihedral group using this whole left coset equals right coset business in complete generality for all n would be very time consuming. So we're actually going to use the closed under conjugation approach. So what we need to check is that G inverse HG is an element in H for all G and G and all H and H. In our case, the role of G is Dn, and the role of H is our cyclic subgroup, which means that every little h is a power of R, and every G is either R to the J, some rotation, or SR to the J, some reflection. Note here I'm using J because it's not necessarily the same power as I. So what do we want to show? We want to show we're closed under conjugation. So we see that there are two cases. The first case is we're going to conjugate a rotation by another rotation. So let's see what happens when you conjugate a rotation by a rotation. Notice what this means geometrically. It means you're going to do a clockwise rotation by some amount, another clockwise rotation by j times, I times, and then counterclockwise j times. And that's exactly what we're seeing. R to the j, R to the I, R to the minus j. And what happens if you were to do one direction j times, followed by I times, followed by backwards j times? If you actually get it out, polygon and try it, you'll see that you get the same result as if you only did it clockwise I times, because the clockwise j times and the counterclockwise j times cancel each other out, because when you're doing only rotations you have commutativity. And why? Because here you're actually working entirely in the cyclic subgroup itself. So we're closed under conjugation by R to the J. So we had the other case. What happens when you conjugate a rotation by a reflection? Well, let's use our calculations to see what happens. First, well, the inverse of a product is the product of inverses. The inverse of a reflection is itself. So S inverse is S. Obviously, we can't really figure out which element this is when we have two S's in the middle like that. So we need to move them all the way over to the left to get it in this standard form. So let's move this S out to the left. And that replaces R to the negative J with R to the J. So that's R to the I plus J. Let's move this S out too. So now it becomes negative I plus J. S squared R to the negative I minus J plus J. Negative J plus J cancels and S squared is the identity, so you end up with negative I. So you end up with a rotation. So we do actually see we're closed under conjugation. So the punchline is that this is in fact normal because it satisfies the definition. Although if you want better intuition, it's kind of weird we've got this kind of formula, right? It is worth pointing out that this is a reflection that has order 2. So in fact, that was true from the get-go, that it is its own inverse. So you could have done the calculation a slightly different way. But this does tell you something interesting. If you do a reflection across some axis, a clockwise rotation by a certain amount, and then a reflection across that same axis, that is equivalent to just doing a counterclockwise rotation. For our next example, we will show that the alternating group is a normal subgroup in the symmetric group. Remember, of course, that the symmetric group is the set of all permutations. And the alternating group are the even permutations. Which means what? It means this fact, that when you decompose an element in AN as a product of transpositions, that the number of transpositions is even. What does it mean to be normal? Well, it means that you should be closed under conjugation, so that's what we're going to check. So let tau be in the alternating group. So tau can be written as a product of an even number of transpositions. And let sigma be in the symmetric group. What do we want to prove? We want to prove that sigma inverse times tau times sigma is even, which means that we want to prove that it can be factored as a product of an even number of transpositions. So one way to show that, of course, is that we should write down a factorization for sigma. So suppose sigma is equal to sigma 1 to sigma k, and tau is equal to tau 1 through tau 2j. Factorizations into products of transpositions. Notice we do not know if k is even or odd, because it's an arbitrary permutation. Let's see what happens when we do this calculation. Well, sigma inverse is the inverse of sigma 1 to sigma k. Tau is tau 1 to tau 2j, and sigma is sigma 1 to sigma k. The inverse of a product is the product of the inverses in reverse order. Or I should say the reverse of the product of the inverses, so sigma k to sigma 1, all inverted. The inverse of a transposition is itself. And so this conjugate is actually this product of transpositions. How many terms are there? There's 2j, there's k, and there's k. So there's 2k plus 2j, 2k plus j factors here, which means this conjugate can be written as a product of an even number of transpositions, which means that it is in fact an alternating permutation. So conjugates of alternating permutations are alternating. Ergo, the alternating group is a normal subgroup of Sn.